Testing. All right. Okay. Another session. Let's do it. Okay. So, yesterday we wrapped up our first. Well, not we didn't wrap up, but we wrapped up a good milestone of our first project in that we were able to generate a web page in a custom manner, like where we had this set of command line options that a user can provide arguments to actually generate a custom web page that sort of looks like this. Now, as you can see here, we have a lot of code written. It's a good 84 lines, and I think that's actually the largest program we've written in C so far together. And yeah, there's a lot going on in here, and we need to sort of think about how we can break this down into more manageable pieces, like make it more modular with functions and things like that. But as I was working on this, I realized that that's actually going to be a good like transition point back to our book, because that's actually where we stopped at, right? Where chapter four? Where's chapter four? Right here. Where it says, "Oh, using multiple source files, break it down and build it up." So let's just do that. Let's just continue forward with the book, and then we'll come back to the project and work on it more. So I'm gonna clean up my workspace here because it's too many windows again. And let's see here. Yeah, let's just start closing stuff because there's too much going on. Okay, so hopefully this is not a hard chapter. Okay, so if you create a big program, you don't want a big source file. Can you imagine how difficult and time consuming a single source file for an enterprise level program would be to maintain? In this chapter, you'll learn how C allows you to break your source code into small, manageable chunks and then rebuild them into one huge program. Along the way, you'll learn a bit more about the data type subtleties that get to meet your new best friend. Oh, and get to meet your new best friend. Make. Guess the data type. So C can handle quite a few different data types: characters and whole numbers, floating point values for everyday values, and floating point numbers for really precise scientific calculations. You can see a few of these data types listed in the opposite page. See if you can figure out which data type was used in each example. Remember, each example uses a different data type. So I guess the total number of components in the rocket, I would say that's like an int, maybe. I don't know. I don't know how to make rockets. So for sure, there are more than like they're probably like more. All these nuts and bolts are probably hundreds already, and then you have all these other things internals, and you get into thousands, and so I'm guessing an int, and the amount of fuel the rocket will need is probably a short, because I'm pretty sure we don't need over 65,000 gallons of fuel, do we? Let's see. Amount of fuel a rocket needs. Let's see. So a rocket, let's see. What kind of fuels are, let's see. Oh yeah, fine. What's the formula to calculate how much fuel is needed for a rocket? Does it even tell us? Oh, too much math. Too much math. This is where we need AI. Let's see. Chat? Say hello to DuckDuckGo AI chat. Get started. Let's go for GPT 4.0 mini. I agree. Whatever. Amount of fuel rocket needs. The amount of fuel a rocket needs depends on okay, fine. Saturn IV rocket needed about, I guess it had capacity of 740,000 gallons. Okay, definitely an int because a short is also 65. It only goes up to like 65,000 or something, 2 to 16. So let's see. The distance from the launch pad to the star, Proxima Centauri, that's a long for sure. The number of stars in the universe that we won't be visiting, a long. The number of minutes to launch, short. Each letter on the countdown display, that's a character, right? Char. Okay, fine. Total number of components in a rocket. Oh, okay. I guess. Wait, we did say it. Yeah. And then the amount of fuel the rocket will need is a float. I guess it's true. We could have like point 0.5, like whatever, like 700,000 0.5 gallons. Darn. Uh, a double. Oh yeah, distance. I keep thinking in whole numbers. Double, yeah, because double is a 64-bit precision number, so it should be very, very large. But yet you still get the floating pointiness of it. The number of stars that we won't be visiting, yep, long. Number of minutes to launch, short, yep. And each letter, yep, char. We got that at least. Cool. Anyway, yeah, here's a quick guide to data types. Basically, yeah, just read it. But ints are usually 32 bits nowadays. Shorts are usually 16 bits. Long are 64 bits. Floats are 32 bits, and doubles are 64 bits. So double is this is exactly like a float, except just more precise because you have more bits to represent the number. Okay. Okay. Now, next. Don't put something big into something small. Yeah, this is very important about like data types because even though like something like a long or int, they are sort of the same type of thing. They're both integers. Um, if you have like a long that is way more than 4 billion or whatever the maximum number an int is, you lose precision when you try to treat that long number as an integer. Like it gets truncated, right? Because you only have, like, for example, for sure, if you have a long number that's like 64 bits, even though it may not occupy all the 64 bits to represent it, let's just say 40 bits, for example. If you try to represent that as a 32-bit integer, you're gonna lose like those extra 8 bits, and all of a sudden you get a completely different number. So this is the discussion here. Let's read it. So don't put something big into something small. When you're passing around values, you need to be careful what the type of the value matches the type of the variable you're going to store it in. Different data types use different amounts of memory. So you need to be careful that you don't try to store a value that's too large for the amount of space allocated to a variable. Short variables take up less memory than ints. True, because shorts are 16 bits, so it's only 2 bytes to represent a number, versus 4. And ints take up less memory than longs. Yeah, 4 bytes to 8 bytes. Now, there's no problem storing a short value inside an int or long variable. Why? Because an int is 32 bits, a long is 64 bits, but a short is only 16 bits. So if you try to put a short value into an int or a long, right, container, or basically a variable, it's going to fit in just fine because 16 bits is way less, right? So you're not going to lose any bits during that process. So there's plenty of space in memory and your code will work correctly. So we can imagine it like this, like visually, right? So let's say I have memory again, and here's just 1 byte each, right? So one of these is 1 byte. Okay. Okay. Now, if I said something was a long, for example, I would have 1, 2, 3, 4, 5, 6, 7, 8. So I would have all these bytes here to represent the number. If I said something was an int, for example, I would have all of these, right? Now, if I try to fit a short into an int or a long, I would just need 2 bytes right there. So that's why it fits. But the other way around, let's say I want to fit a long to an int right here. Well, guess what? If let's say I needed these extra 8 bits, right? I wouldn't be able to fit it because an int only goes up to this range right here, these 4 bytes. Oh, I should have just done this, right? So you lose the rest here. Okay, so like here's an example code, right? You have 15 as a short value, but then you assign whatever's in x to an integer y, and you'll still get 15. And here's like the analogy: the contents of a short will always fit into an int or long. The contents of a long may be too large to fit into a shortened int. Yeah, see, something like this big can't go into here, these cups, right? So the problems start to happen if you go the other way around. Is say you try to store an int value into a short. So you have this number here that's an integer. I think it's 100,000. That's like way bigger than the maximum amount for a short. And you try to assign that back into a short. You are going to get a really different number because it's truncated. And in here, it's actually going to be negative 31,072. Sometimes the compiler will be able to spot that you're trying to store a really big value into a small variable and then give you a warning. But a lot of the time, the compiler won't be smart enough for that and it will compile the code without complaining. In that case, when you try to run the code, the computer won't be able to store a number 100,000 into a short variable. The computer will fit in as many ones and zeros as it can, but the number that ends up stored inside the y variable will be very different from the one you sent it because, trying to fit it in. So, okay. So why did putting a large number into a short go negative? Well, numbers are stored in binary. This is what 100,000 looks like in binary. So you have 100,000 that looks like this, right? But when the computer tried to store that value into short, it only allowed the value a couple of bytes of storage. The program stored the right-hand side of the number. So it only stored this right here. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it only stored this part here. And, when we're talking about binary, that last most significant bit is actually what we call the sign bit. So if it's like 1, it indicates a negative number, and if it's 0, it will indicate a positive number. So signed values in binary beginning with a 1 in highest bit are treated as negative numbers, and the shortened value is equal to this in decimal. So using casting to put floats into whole numbers. What do you think this piece of code will display? Let's see. Int x is 7, int y is 2, float 7 over 2. So these two are integers, right? Integer divided by integer. I know this one already. 7 over 2. Well, I think that's going to be 3. And it is. Well, it's because x and y are both integers. And if you divide integers, you always get a rounded off whole number. In this case, 3. So what do? You want to perform calculations on whole numbers and you want to get floating point results. Well, you could either store the whole numbers into float variables first, but that's a little wordy. Instead, you can use a cast to convert the numbers on the fly. So we'll basically convert these integers into float numbers here, right? So this 7, actually, when you cast it, it's going to be 7.0. And y, when you cast it, is going to be 2.0. And 7.0 and 2.0, if you divide that, then you'll get like 3.55 or 3.500000, because you forced the compiler to kind of interpret this as a floating point number. So this float cast will cast an integer value into a float value. The calculation will then work just as if you were using floating point values the entire time. In fact, if the compiler sees you're adding, subtracting, multiplying, or dividing a floating point value with a whole number, it will automatically cast the numbers for you. That means you can cut down the number of explicit casts in your code. So it means that like you don't have to cast both of the numbers. As long as one of them is a float, the other number will kind of get upgraded, right? Because a float is, I guess you could think of it as like priority. Floats will take priority over integers. So if you have a float casted into a number, you do an operation on an integer, it's going to be interpreted as a floating point number, the result that is, right? So you can put some other keywords before the data types to change the way the numbers are interpreted. So unsigned. The number will always be positive because it doesn't need to worry about recording negative numbers. Unsigned numbers can store larger numbers since there's now one more bit to work with. So an unsigned int stores numbers from 0 to a maximum value that is about twice as large as the maximum number that can be stored inside an int. There's also a signed keyword, but you almost never see it because all data types are signed by default. So they give us an example here, but I'm going to also kind of just make that point. So in C, we have something that's like int, right? X. And so when we say int X, it's actually a signed int, meaning that we have the concept of a number line, right? Going from some negative number to all the way to a positive number. And how that works is when we actually represent the numbers as zeros and ones, right? 1 0, 1 blah 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 blah, and then 1 0 0 1. This first bit here indicates whether or not something is positive or negative. So if it's a 1, that means a number is negative, right? If it is a 0, that indicates a number is positive. In effect, if we say that in the space of an int where it's like 32 bits, we have this many combination of numbers. Okay? But when we make something signed, essentially we've actually split the thing in half. Okay? So this will be like around, well, this is about 4 billion, right? 4 billion or so numbers. Okay? So when we split this in half, means we have 2 bill here and then 2 bill here. Okay? So then you go from negative to B to positive to B. And that's the regular int. That's signed int. Now, in C, we don't always have to declare something as int X. We can also say unsigned int X. And that actually then makes the number line look more like this. Me clicking around again. Okay. Okay. Starting from 0, now all the way up to having 4 billion numbers. So our range here is really, truly, positively 2 to the 32. Straight up. And this is useful for things like, array indexes or like anything that, a number that can never be negative is appropriate for unsigned int, and that allows you to have literally more numbers to represent as that integer. In this case, it doesn't matter, right, whether or not this is positive or negative, or 1 or 0, because 0 is still meaning it's a positive number. 1 still means it's a positive number, because negative numbers aren't possible in this type of interpretation. But it only works if you give C the hint that something is unsigned. So that's what unsigned means. So there are various like data types you can do unsigned, right? You could do unsigned. What do you have? Int. You also have unsigned long. You know, unsigned character, and so forth. Okay. Now for long, you can prefix a data type with the word long and make it longer. So a long int is a longer version of int, which means it can store a larger range of numbers. And a long is longer than a long. But you can also use long with floating point numbers. So long double will be a really, really precise number. Okay? Okay. So there's a new program helping the waiters bus tables at the Head First Diner. The code automatically totals a bill and adds sales tax to each item. See if you can figure out what needs to go in each of the blanks. Note, there are several data types that could be used for this program, but which would you use for the kind of figures you'd expect? Well, total would be probably like a float. Count would be an int, and then tax percent. To me, it looks like it should be a float. And then this function here, this add with tax already, if I see add with tax, it should return most likely a float, because we look at the tax, if we're calculating the tax rate, it looks like we want a float here. And then this will probably be like a 0.0, right? And then we return a float. So this will be a float too. So float, int, float, 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 f, or 0.0. And then this val, where does it get assigned to eventually? Let's see. Val is a float because it's being used as a param or an argument to this method. So that is also a float. So let's see. Ah, man, really short. Oh, okay. And this is a short? Oh, that's interesting. Oh, well, because they... Wait, let's check. So I know this is a float. This is a count because we won't be putting that many items into the order. That's fair. But for tax percent, it's a short. I would have assumed it'd be a float because we're doing a tax percentage. It could be like 6.25, right? I mean, I live in a state where it's a fractional tax rate. But to be fair, I guess they made it a float here with a 0.0. Okay, but we still got these right. Float, float, float. Okay. Data types, sizes up close. Data types are different sizes on different platforms, but how do you find how big an int is or how many bytes a double takes up? Fortunately, the C standard library has a couple of headers with the details. This program will tell you about the sizes of ints and floats. So it's a simple program. Basically, we include this limits.h, which is a header that will have special variables that tells us what's the maximum value of a specific type, like integer, int max, right? Int min, float max, float min, and so on. Oh, float.h will also do that too for floats and doubles. Okay, so yeah, here's the, when you compile and run this code, the maximum int is like 2 billion something. Int will be -2 billion, and then float will be like this really big number. And yeah, float takes 4 bytes. Size of int, size of float. Remember the size of operator? Yeah, that tells us the size in memory something takes. Um, so we also have, not only that, we have char, double, short, and longs. I'll leave it up to everyone to just type this out and see for themselves. Okay, there are no dumb questions. Why are data types different on different operating systems? Wouldn't it be less confusing to make them all the same? That's a good question. C uses different data types on different operating systems and processors because that allows it to make the most out of the hardware. So it has to be like platform independent. In what way? When C was first created, most machines were 8-bit. Now most machines are 32 or 64-bit. Because C doesn't specify the exact size of its data types, it's been able to adapt over time. And as newer machines are created, C will be able to make the most of them as well. So what do 8-bit and 64-bit actually mean? Technically, the bit size of a computer can refer to several things, such as the size of its CPU instructions or the amount of data the CPU can read from memory. The bit size is really the favorite size of numbers that the computer can deal with. So, like, if I say a computer is 32 bits, that means it naturally wants to operate in 32-bit chunks. Same for 64-bit. And I think the bitness is really mostly in reference to um like, I don't know, like throughout my, I guess, career, I've always heard it like be referred to the number of bits it can send and receive through like memory, like data access, and how big it interprets data natively. Not exactly the instruction size, because like I think like even like x86 CPUs, like the instruction size can vary, right? So I think it has more to do with like sending how big the data you can send back and forth in one shot in memory. So what does that have to do with the size of ints and doubles? If a computer is optimized best to work with 32-bit numbers, it makes sense if the basic data type, the int, is set at 32 bits. I understand how whole numbers like ints work, but how are floats and doubles stored? How does the computer represent a number with a decimal point? It's complicated. Most computers use a standard published by IEEE. Yeah, it is complicated, and I don't think that's something we'll get to here in this, at least this round of learning. Do I really need to understand how floating point numbers work? No. The vast majority of developers use floats and doubles without worrying about the details. That's true. I don't know all the details. As like a developer, I know how to use floats and doubles and I know like the differences and all that stuff, but I don't know like the exact implementation details of how that's actually working underneath the hood. Anyway, uh, oh no, it's the out of work actors. Some people were never really cut out to be programmers. It seems that some aspiring actors are filling in their time between roles and making a little extra cash by cutting code, and they've decided to spend some time freshening up the code in the bill totaling program. By the time they rejiggered the code, the actors were much happier about the way everything looked. But there's just one tiny problem. The code doesn't compile anymore. Oh, so here's the code. So let's see what happened to the code. This is what the actors did to the code. You can see they really just did a couple of things. Really? Well, how about we type it out? Let's see what's wrong and try to understand it as we go along. So was it bill total? We call it bill total program. Oops. Let's call it billing. Yeah. Billing. Main.c. Okay. Include stdio.h. And what did it say here? Float total. It's going to be 0.0. We have change my desk. So okay, we have a short count. That's going to be 0, and then see, this is okay. This is a comment, so it's gonna be short tax percent. It's gonna be 6. And then we'll have a main, and then that's gonna have full val, print f, price of item. Then we'll have while scanf. We're scanning for a float number. Then we'll pass in the address of val to, I guess, put in the price of that item. And then we have to expect it to read one item successfully, which that's what we're asking for. Then we'll print f total so far. It's going to be a formatted floating point number. Looks like we want to make it look like money with a .2f. And then add with tax val. Then we'll print f again. Price of item. Okay, so that's there. It's gonna ask again on the next for the next round. Then what we want is we want to print f final total percent .2f. So make it look like money again. The total amount. Then print f the number of items. What's hi? HIN. New line. Count. What is H? Okay. Then let's see here. We return 0. So that's the main function, and then now we actually write our helper called add with tax. I see where this is going. I know the bug. Add with tax float f. Okay, and then we'll have float tax rate equals 1 plus tax percent. Then we divide by 100.0 because tax percent happens to be a short, and we need to make sure this evaluates so long. So adding a 0.0 at the end will guarantee us that. Total. So total is defined all the way up here, so it's okay to just access it down here. F times tax rate. Finally, count equals count plus 1. So we add that number to our total amount of items. Turn total. Okay, cool. So it's just basically a program that continuously asks us for prices of items, and then it'll just total as we keep inputting more and more prices into, I guess, some running sum. So they changed the order of the function. Okay, so there shouldn't really be a problem. The code should be good to go, right? Well, everything was great, right? Up until the point that they compiled the code. So let's compile it ourselves too. CD billing main, oops, GCC main.c. Ooh, we get some bad stuff. Okay, so we're saying, okay, implicit declaration of function add with tax. Warning, format %f expects the argument type double, but argument 2 has type int. Huh? Argument 2? Huh? Right here? Why is it an int? It's saying that, this is supposed to be a float because we're formatting as a float, but this function call is returning us an int. So that's weird. Conflicting types for add with tax. So what we have is a float that takes in a float. Confusing. Let's see. So they have the same error too, right? So what's going on? So that's not good. What does the error conflicting types for add with tax mean? What is a previous implicit declaration. And why does it think that the line that prints out the current total is now an int? Didn't we design that to be a floating point? The compiler will ignore the changes made to the comments, so that shouldn't really make a difference. So the comments that the actors added here in the program is what they're referring to. Okay. Well, then the only thing they did was they changed the order of the functions. But if the order is the problem, why doesn't the compiler just return a message saying something like this? Dude, the order of the functions is busted. Fix it. Seriously, why doesn't the compiler give us a little help here? So it's like, the expectation is like, okay, if we change the order of the functions, why didn't the compiler complain to us? Like, why didn't it stop us from compiling the program? So to understand exactly what's happening here, you need to get inside the head of the compiler for a while and look at things from its point of view. You'll see what's happening is that the compiler is actually trying to be a little too helpful. Okay, so far, like, let me just try to level set. What's going on right now is that the compiler is having problems with actually truly finding the real add with tax function here, because this add with tax is actually being defined after the main function. So what's happening is that the compiler is actually guessing what type this is, even though it hasn't seen it yet at the point where the compiler is like scanning for code, right? As it's scanning for code, it comes across with this add with tax and goes, oh wait, I don't know what the signature of this is. Like, what does it return? What type of arguments it's taking, and things like that. So what's happening is that, spoiler alert, it just guesses and tries to assume that it's an int. It's like this function here is going to return an int, and you're going to take an int. And as it turns out, I think that's like the default behavior of C compiler, is that if you are writing a program where you didn't define a function yet, and you attempt to call it before it's defined, there's assumption that it's most likely going to be an int in this case. And that's the reason why you would want to move this one up to before you actually use or call the function, so that it's already technically defined. So yeah, I'll go into more detail after we read a little more. So compilers don't like surprises. What happens when the compiler sees this line of code? Printf total so far. Okay, so that's the offending line that we have, right? So the compiler sees a call to a function it doesn't recognize. Rather than complain about it, the compiler figures that it will find out more about the function later in the source file. The compiler simply remembers to look out for the function later on in this file. Unfortunately, this is where the problem lies. Hey, there's a call to a function. I've never heard of it, but I'll keep a note of it for now and find more later. Okay? The compiler needs to know what data type and the function will return. Of course, the compiler can't know what the function will return just yet, so it makes an assumption. The compiler assumes that it will return an int. Meh, I bet the function returns an int. Most do, which is true, so that's why it's making that assumption. So when it being the compiler, when the compiler reaches the code for the actual function, it returns a conflicting types or add with tax error. So actually the conflicting types comes from when it finally encounters, like, it's scanning, right? And then it finds this reference here, this call here, and it says, okay, I haven't seen it yet, it's going to be int. And it keeps scanning, and then it sees this real add with tax here, but it's already made that assumption, so it's too late, and it goes, oh, I got a conflicting type here. It's the same method, or same function name, but it's a different type. I don't know what to do. So let's read that again. When it reaches the code for the actual function, it returns a conflicting types for add with tax error. This is because the compiler thinks it has two functions with the same name. One function is the real one in the file, and the other one is that the compiler assumed that will return an int. So that's the one it's conflicting with, the one that where it assumed that the function will return an int. So the compiler goes, a function called add with tax that returns a float, but in my notes it says we've already got one of these returning an int. So that's the reason why we end up like that, right? So yeah. So here's some thinking here. The computer makes an assumption that the function returns an int, when in reality it returns a float. If you were designing the C language, how would you fix the problem? I mean, like I said, I think we just move it up top. So you could just put the functions back in the correct order and define the function before you call it in main. Okay. Changing the order of the functions means that you can avoid the compiler ever making any dangerous assumptions about the return types of unknown functions. But if you force yourself to always define functions in a specific order, there are a couple of consequences. Interesting. So we can't just easily do that all the time. Okay, let's read the reasoning why we can't just always simply solve it by moving the function up. Fixing function order is a pain. Well, we actually before that, I'm gonna just demonstrate what happens if I move the function up. Okay, so then we'll kind of listen to the opinion of head first or the book in this case. So I move the function up. Now I have this defined, so when I'm compiling, the compiler will see this and go, okay, cool. Add with tax is a function that takes in a float and returns a float. All good. I'll continue on and continue on, find add with tax. Okay, I've seen this before. It is actually this function here where it takes in a float and returns a float. Great. I'll keep going. Right. So that's the good scenario, and let's see if it works. See, all good, all clean, and we can just total so far. Wow, that's totally wrong, but okay. Weird. Price of an item 3.45. Total so far is 3.66. Why? Anyway, let's see. Let's do 1.00. Wow, this is so inaccurate. But okay, that's supposed to be 5.96 or whatever. But I think it's because we typoed somewhere. Oh no, tax rate. It has to consider tax rate. I forgot. Okay. But anyway, so yeah, apparently we can't always move functions up to solve the problem. So let's see what's going on. Why is that not the best solution all the time? So fixing function order is a pain. Say you've added a cool new function to your code that everyone thinks is fantastic. So int do whatever, float do something fantastic, int do stuff. Sure. What happens if you then decide your program would be even better if you add a call to the do something fantastic function in the existing do whatever code? So you want to add a call to do something fantastic inside the do whatever. So inside do whatever, we want to do something fantastic here. See where this is going? Yeah. So then you will have to move the function earlier in the file, right? So we have to move this one above this do whatever so that the do whatever inside can actually do something fantastic. Huh. Most coders want to spend their time improving what their code can do. It would be better if you didn't have to shuffle the order of the code just to keep the compiler happy. Yep, that's okay. That's fair. Like you have to start like moving stuff around all the time, and then when you change code inside another body, you're like, oh, okay, where do I move the other function now? So fair. Okay. So here's another one. In some situations, there's no correct order. So in this situation, it's kind of rare, but occasionally you might write some code that is mutually recursive. So ping, pong will then call back to ping, and then ping will call pong, and so forth. So it's like this. So if you have two functions that call each other, one of them will always be called in the file before it's defined. For both of those reasons, it's useful to be able to define functions in whatever order is easiest at a time. But how? So you'll split the declaration from the definition. Wait a second. Or maybe I'm thinking JavaScript. Okay. Okay. Split the declaration from the definition. Remember how... Okay, so again, let's go back. Something to declare something is like this, right? To define something is like this, to assign a number to a variable. So to declare something, we want to kind of like bring it to life by saying, hey, X is an int, but I haven't had a value yet. To define or initialize is just to assign. So to declare and define and initialize is basically giving it the declaration and then the definition. Okay? So the same thing with functions, right? So this is actually to declare and define the function. Now, if we just wanted to declare the function, we can do something like this. Right? We just define the signature, and then we just implement it later. And I think just like the way it's done, like, oops, what did I do? Okay. Float add with text, float add. So this would actually still compile and run just fine. Okay? So what people generally tend to do in C for simpler programs is that they want these things to be at the bottom of the file, right? Like this definition. And so what they do is they keep the declaration up on top, and then they actually throw the definition at the bottom. And so when the compiler is actually scanning the file, it encounters this declaration, right? And then it makes a note of it, just like how it did when it made the assumption. And so when it finally encounters this code here, where we call add with tags, it goes, oh yeah, no, I've seen this declaration before. It's up here, and that's why it's fine. Because the definition of this function is actually a separate thing where eventually all this gets stitched together in compilation. So that's why this works. And you'll see that too in like maybe, if you ever see smaller C programs or like homework or something like that. So yeah. So split the declaration from the definition. So remember how the compiler made a note to itself about the function it was expecting to find later in the file? You can avoid the compiler making assumptions by explicitly telling it what functions it should expect. When you tell the compiler about a function, it's called a function declaration. So this right here has no body. It just has the signature. The declaration is just a function signature, a record of what the function will be called and what kind of parameters it will accept and what kind of data it will return, what type of data. So once you've declared a function, the compiler won't need to make any assumptions. So it won't matter if you define the function after you call it. Okay? So if you have a whole bunch of functions in your code and you don't want to worry about their order in the file, you could put a list of function declarations at the start of your C program code. So you see all this, do something fantastic and all these things here. So even better than that, C allows you to take that whole set of declarations out of your code and put them into a separate header file. You've already used header files to include code from the C standard library like this. Include angle brackets, stdio, angle brackets. So what this does is it actually gets all the contents of stdio.h and just places it into your code. And like it's kind of like just like a copy paste. So this is actually just like a little like like a command to tell the compiler, hey, get everything from stdio and just slap it on top here, like all the contents. That's how I think of it. So yeah, see this line will include the contents of the header file called stdio.h. And remember, if we want to see what that is, we can control click into it from our IDE. And yeah, that includes is equivalent to kind of just like copying and pasting all of this into this file. So yeah, let's see how we can go about creating our old header files. So creating our first header file. To create a header, you just need to do two things. Create a new file with the .h extension. So if you're writing a program called totaler, then create a file called totaler.h and write your declarations inside it. Okay, so simple as that. So we'll just create a main.h and then we'll add our declaration here. So does the ink work? Does the ink work like this? Cool, it does. Okay, cool. So we have that, and we don't need this anymore, right? So we can get rid of that, and we'll save. Then we'll save this one too. And then now what do? We just include our header in the main program. So then we could just include with quotes our header file. Okay. So now what we had done is we've just said, since we're including main.h, we're getting the contents of here and just slapping it on here. It's a pretty good way to think about it, right? So when you write the name of the header file, make sure you surround it with double quotes rather than the angle brackets. Why the difference? When the compiler sees an include line with the angle brackets, it assumes it will find a header file somewhere off in the directories where the library code lives. But your header file is in the same directory as your .c file. By wrapping the header file name in quotes, you are telling the compiler to look for a local file. When the compiler reads the pound include in the code, it will read the contents of the header file just as if it had been typed into the code. Separating the declarations into a separate header file keeps your main code a little shorter and has another big advantage that you'll find out in the next few pages. Okay, for now, let's see if the header file fixed the mess. Sure, let's do it. So let's compile again. And let's try it out. Oh, it looks like it works. I mean, 1.78. It works. I mean, it found it because, again, including the header files, like just like slopping contents in. So, works. So the compiler reads. Okay, yeah, now it works. So be the compiler. Look at the program below. Part of the program is missing. Your job is to play like you're the compiler and say what you would do if each of the candidate code fragments on the right were slotted into the missing space. Okay. Oh, okay. Got it. So we had to, given this, will this compile and whatever, will it be problematic? Stuff like that. Okay, so sure. All right, so include stdio, and then this is going to be part of the main here. Mercury day and Earth days, hours and Earth days. They are defined here, and then so we define them up here with ints here. Okay, and then we use it in our main function, and that looks like it should work. So I say we can compile the code. And will the program work? Yes. Okay. Float Mercury day and Earth days is the only one that's defined ahead of time or declared ahead of time. Okay, well, we know we can compile the code, that's for sure, because down here is going to have hours and Earth Day, but it's not in up here. But this is a trick question because remember, if let's say we're scanning, we found this declaration, we're okay, we move on to main, we find the usage of it, we found that it was already declared, and then we move on to this line where we reference this hours in an Earth Day function. Well, the thing is that since we've never seen it before, as the compiler, we're going to make the assumption that we've never seen this before, but most likely it's going to be an int, right? It's going to be an int. And then as we keep scanning and scanning, we're going to encounter this definition where it is still an int. So yes, the code can compile, and yes, the program will work. I'm leaning towards it won't display a warning too, because by the time we only got warnings whenever we encountered something that contradicted what the compiler assumed, right? But in this case, when we encounter this function definition, right, when we finally have this here, it's not contradicting what the compiler assumed to be. So I would say it won't display a warning. So yeah, that's my take on it. This one is going to display a warning for sure. This program won't work. I don't think so because it's assuming that it's int when we didn't define it. So yeah. Here, this one. What's the difference between this one? Oh, okay. So this one is assigning the result of Mercury day and Earth days to an int. So that's like kind of downgrading it. The program won't. I mean, the program. I don't know what it means by work, right? Does it run or does it not run? Does it give us the result, not the result? So we can compile the code. I think we'll get a warning on the types mismatch, and the program will run, but it won't really work correctly. So solutions. Yep, yep. Okay, and then it should display a warning. Oh, that's interesting. Okay. So it will display a warning then. Okay, fine. I'll take it. Something new. Okay. Display a warning. All right. And so the program won't work, and I guess we can't compile. Okay. Wait, last time were we able to compile? Probably not, huh? Okay. I totally missed that. Okay. I wasn't attentive enough, but yeah, I guess it won't compile if those assumptions are made. And in this one, we can compile the code. And I guess what they mean by the program will work is if it's correct in this case. Because this will run, but it's not gonna work in terms of being correct. Anyway, there are no dumb questions. So I don't need to have decorations for int functions. Not necessarily, unless you are sharing code. You'll see more about this soon. So I'm confused. You talked about the compiler pre-processing. Why does the compiler do that? Strictly speaking, the compiler just does the compilation step. It converts the C source code into assembly code, but in a looser sense, all of the stages that convert the C source code into the final executable are normally called compilation, and the GCC tool allows you to control those stages. The GCC tool does the pre-processing and compilation. So what is the preprocessor? The pre-processing is the first stage in converting the raw C source code into a working executable. Pre-processing creates a modified version of the source code just before the proper compilation begins. In your code, the pre-processing step reads the contents of the header file into the main file. So actually, this is actually not like real C code. These are just like little like macros, I guess, for um the like this pre-processing step to operate on, like to tell what to do to kind of generate the real C code before shooting it to the compiler. Um, so does a preprocessor create an actual file? No, compilers normally just use pipes for sending the stuff through the phases of the compiler to make things more efficient. Why do some headers have quotes and other have angle brackets? Strictly speaking, it depends on the way your compiler works. Usually quotes mean to simply look for a file using a relative path. So if you just include the name of a file without including a directory name, the compiler will look in the current directory. If the angle brackets are used, it will search for the file along the path of directory. So think of it as like quotes as like local, and then the angle bracket is like that predefined system directory to find the header files. So what directories will the compiler search when it is looking for header files? The GCC compiler knows where the standard headers are stored. On a Unix-style operating system, the header files are normally in places like USR, local include, or USR include, and a few others. So that's how it works for standard headers like stdio.h. Yes, you can read through the stdio.h file in a Unix-style machine in USR include stdio.h. If you have the MinGW compiler on Windows, you can find it in this path. Okay, I'm excited. Where's this at? User include stdio. Oh, it's exactly what they said. So it is here. Interesting. So, can I create my own libraries? Yes, you'll learn how to do that later in the book. Cool. So yeah, this is important points to remember. Think this one's important. Function declarations tell the compiler what your functions will look like before you define them. If you try to call a function before you define it, there can be problems. And the compiler will treat included code in the same as code that's typed in the source file. Okay. Not much. I mean, this is exactly what we just read, like for the past few pages. And here's like the list of reserved keywords in C. It means that you can't use these keywords. Like you can't use these words as like variable names, for example. Like you can't declare a variable name to be int. You can't say like int, where int is the variable name. So these are like reserved. You can't use them. They're part of the C programming language. So okay. How much do we have left? Ooh, still have quite a bit. Okay. So I'm gonna stop here. Yeah, I'm gonna stop here. I think we learned quite a bit. So I'm going to commit this. Okay, cool. Great. Cool. I'll stop here and then we'll probably finish the rest tomorrow. Let's see. I'm super happy. We're making good progress. Look at that. Let's see. Ooh, I think we'll do some make stuff. Yeah, how make tool works. Cool. Okay, it'll be interesting. Alrighty. Guess that's it.